Before anyone can design a skyscraper or figure out a flight path to Mars or even get into the cool stuff in trigonometry, we have to start with the absolute basics. So today, we're going to learn the fundamental language we use to describe space itself.
It's a pretty big question, right? But it's one we answer all the time. Think about a surveyor mapping out a new piece of land, or a pilot trying to navigate through a storm. They're all using the basic components of space to do their jobs. So, ready to build this thing from the ground up?
So here's our game plan. We're going to start with the absolute atoms of geometry, then put them to the test with a few puzzles. After that, we'll cover the one mistake you absolutely have to avoid, and finally, we'll see how all these ideas are basically the blueprints of our world. Let's dive in. We are literally starting from scratch here. We're going to take a zero-dimensional point, just a tiny speck in space, and stretch it out into a one-dimensional line. And then we'll see how those simple building blocks come together to create a two-dimensional angle. These are the atoms that build everything else we're going to talk about. Okay, this is where it all starts to click. First, you have a point. It's just a location, 0 dimensions, like a single star in the sky. If you stretch that point in opposite directions forever, you get a line. Now, if you just chop out a piece of that line, you get a line segment, which has two distinct endpoints, kind of like the edge of your desk. But the one we really need to focus on for what's coming up is the ray. It has one endpoint and then extends forever in just one direction, just like a beam from a flashlight. And this is where the magic happens. You take two of those rays and you make them share an endpoint. Boom! You've just created an angle. That shared point is the most important part. We call it the vertex. The two rays become the sides of the angle. It sounds simple, and it is. But this one idea is the foundation for pretty much all of trigonometry. All right, so we've got the lingo down. Now it's time to put on our thinking caps and head into the construction zone to see how these pieces actually fit together. I've got 3 puzzles for you, starting easy and then getting a little more interesting. Let's see what you've got. Okay, let's start with a nice simple warm-up. If you've got a geometric figure that has exactly one starting point but then goes on forever in a single direction, what do we call that? So, what's the secret? It's all in the definitions we just went over. A line goes on forever in both directions, no endpoints. A line segment has 2 endpoints. The only one that fits the bill is a ray. And here's the key. When you write it down, the endpoint, the starting point, always has to come first. Simple as that. All right, let's kick it up a notch. Imagine 3 points plotted on a graph. Now, what happens if we draw 2 rays? One that starts at point A and goes through point P, and another that also starts at point A and goes through point T. What did we just create? The big clue here is right in the notation. Ray AP and ray AT. Notice what they have in common? They both start at point A. And if you remember our definition, when 2 rays share a common endpoint, they form an angle. And that shared point, A, becomes our vertex. And there you go. The structure is an angle, its vertex is at point A, and we can call it either angle PAT or angle TAP. As long as that vertex, A, is the letter in the middle, you are golden. See? Not so bad, right? Okay, time for the final challenge. Let's see if you're ready for this one. Picture 4 points all sitting on the same straight line, in this order, W, X, Y, and Z. The question is, how many totally unique line segments can you make by picking any 2 of those points? Take a second and think about it. So how do we tackle this without getting confused and counting something twice? You just have to be systematic. Let's start with point W and list all the segments we can make from there. We've got WX, WY, and WZ. That's 3. Now let's move to X. We can make XY and XZ. We don't count XW because that's the same segment as WX, so that's 2 new ones. And finally, from Y, there's only 1 new segment left, YZ. So let's do the math. We had 3 from W, plus 2 from X, plus 1 from Y. That gives us 6. 6 unique line segments. It's a really cool example of how just a few simple rules can lead to some pretty interesting results. All right, I need you to listen up because this next part is maybe the most important takeaway from this entire explainer. There is one tiny mistake with naming angles that can cause massive headaches later on, so let's make sure we get this right. Let's be crystal clear about this. If you have an angle where the vertex, the corner point, is point A, you absolutely cannot call it angle BCA or CBA. Why? Because that would imply that the vertex is at C or B, which is just wrong. The middle letter is everything.
So here it is, the golden rule. The vertex must always be the letter in the middle. So for that angle with the vertex at A, it has to be named angle BAC or angle CAB. That's it. Please burn this into your memory. It will save you so much trouble down the line. So you might be wondering, why do we care so much about being this precise? Well, it's because these abstract ideas are the literal blueprints we use to build and navigate the world around us. Let's look at a couple of real-world examples. Ever see a surveyor using one of those laser machines? That laser beam is a perfect, real-world example of a ray. It starts at the machine and shoots out in a perfectly straight line. Or think about a plane's flight path on a map. It's not one continuous line, right? It's actually a whole series of connected line segments between navigation points. This isn't just textbook theory, this stuff is everywhere. So, we've laid the foundation. We started with nothing but a single point, and we built our way all the way up to an angle. So, what's next? What happens when you take these angles we've just defined and stick them inside of a circle? Well, that is where the entire amazing world of trigonometry really opens up. But we'll have to save that for next time.